Okay, so the next thing we're going to do is just complete our assessment of sort of our distribution here, and kind of figure out again whether we think it's defensible to treat this as a normally distributed data set. And so I had my top value was 94. So now what I'm checking is, so I've checked this section, right, and I came out with 72% instead of 68.26. I now want to check the sort of next standard deviation. And if you notice, the way that I do this is simply I take the standard deviation and look at one of those around the mean, and then two, et cetera, right? So that's just how I'm doing this here. I'm saying, okay, 81 plus 13 is 94. Anything that's above 94 obviously is going to comprise my second and third and above standard deviations above the mean. And so if I do this, then I see that I get 90 out of 688 matching rows. And actually, so let's go ahead and look at this here. So I'm going to do 90 divided by, oops, you can see without the equal sign, it doesn't actually do the math, equals 90 divided by 688. Okay, so that's 13%. Now if I look back at my distribution here, I can see that I should expect about 0.13, 2.27. I should be looking at somewhere around, let's say 17% should be more than one standard deviation above the mean. So not exactly, again, but we're looking for sort of a reasonable approximation here. And so now I'm going to do the same thing on the other side, right? So I come back to my Google Refine, and I'm going to look at what is 13. So I started at 68. I need to go 13 below that. It's going to be 55. How many readings I have in there? I have 50. So that's between 1 and 2 standard deviations below the mean. So 50 divided by 688. Right, that's 7%. Not as much as I would expect. What if I do down here, so I had from 55 to 0 is 25 matching rows. And that is a total of, okay, is 3%. So, this is a judgment call. And actually, one of the things that I want to emphasize here is that anytime you're doing statistics, or journalism for that matter, right, you are always making judgment calls. There is no mathematical definition for an outlier. We use these systems as a way of making approximations, of facilitating our own judgment, but there is no magic formula that gives us the answer that something is definitely or isn't the way we expect it to be. And of course, in this case, we have an upper limit. So, based on the basis of this analysis, I feel pretty comfortable that this is a normally distributed data set, that we see what we would expect, which is the vast majority of our values clustered around the middle. We see, some outliers. And so on that basis, I would look at this and say, if somebody said, wow, that high school only has a graduation rate of 70%, I would say, you know what, that's not that unusual. And actually, a value of 90% isn't that unusual. These are well within the expected values that we would consider for the majority of schools, right? The majority of schools fall roughly within that range. So again, this is a way to facilitate making our own judgments about this, and it can also be it's likewise a way for us to say, hey, this is a really unusual data point, right? So if we look down, we might have thought this anyway, but if somebody says, yeah, the graduation rate in this high school is 55% or 50%, that is really low. Statistically, it is extremely unusual. So again, we can say, well, I don't know, is there a big difference between 50 and 75, and between 75 and 100? 50 is a much more unlikely number. It generally means that it is outside of normal. So anyhow, That is sort of the main thing that we're looking at. Now, if this were a skewed distribution, or if I wanted to, I could also compare this to the skew assessment. And in doing so, I would find I would use the median and the quartiles. And we'll look at those in a little bit more detail in class. Likewise, one is lucky because there are also formulas in Excel for that. So median is an option here. And once again, I can choose all of my values. And it will give me the median. One other clue here is that the median is actually very close to the mean, and that is not the case when you have a heavily skewed distribution. In the case of a lot of skew, you're going to find that the median and the mean are very different, and one of the classic examples of this is when we look at things like income distributions. So the mean and the median are pretty close together. That's another good indicator that the mean is an appropriate way to measure what we call the central tendency of the data set. And then we have this, we can do quartile, and now we'll look at a description of which quartiles are which. But basically this is a way to divide up our data set. There are 4 quartiles, as you might have guessed from the quar in that word. And so it is another measure. It's a way that we can look at, oops, yeah, that's not going to like that. And here we go. So that's our array of data, and the quartile we want to say is, whoops, it didn't work at all. Quartile, that is not our data point. That is, right? So again, we're selecting it. By the way, I can also copy this selection as a text. And so I can say, so actually I could also copy just this value directly into my next one. So I can say that the first quartile is there. I can do the same thing. And I can actually copy that. Oops, that didn't work. Should have been able to copy that value in there and perform the other quartiles. And so just to take it, it's obviously just sort of the execution of formulas at that point. And the question is, what does it mean to have quartiles? And the quartiles, oh, they're not on this one. Let's look at this. This is actually one of the things that Wikipedia and Wikimedia are really good for, these kind of reference points. And so there is actually, yeah, I really like, this is actually my favorite graphic of this. Because what it shows also is the relationship between the mean, the median, so a normal distribution. This is showing the relationship between the mean, median, standard deviation, quartiles, and all of these sort of statistics in one place, and how they relate to this normal curve. Now, again, typically we use the median when we are looking at something that is not follow a normal distribution. And what you can see here is this this element, which is this so-called Q3 plus 1.5 times IQR. That's the interquartile range. So it's the number difference between Q1 and Q3. And then this boundary, again, is the kind of boundary that we choose based on how far we can expect things to be from the median. And so again, what this formula gives us is a way to say, hey, something that's outside of this range would be really, really unusual. Now, in a particular data set, you may find that, that one of these measures falls above or below your highest or lowest data value, right? It may actually exceed the range of your readings. And that's okay. It doesn't mean you've done anything wrong. It's just a way of saying, look, you know, if there were something in that category, it would be really, really unusual. The last point that I want to, that I just want to highlight here, and again, we'll go over this again in class, is this concept of so how many standard deviations we are away from the mean. Now, the reason why is this all really valuable? The real reason is that it gives us a way to compare two sets of data that may have different that may have different means, right? So it is quite literally a way to compare apples and oranges, because even though we may not be able to plot them on the same scale, we can compare the values based on how different they are from the average value in the data set. And so I could say that, oh, well, if I have two normally distributed data sets, and I can say, oh, well, this particular value is 2 standard deviations away from the mean for that data set, and this other one is 3 standard deviations away from the mean, then it means that that second reading is much more unusual within its universe than the first one is. I'll show you guys an example. I have to actually find the link, but I'll show you guys an example of how I use this at the journal. It's not that it's a case that comes up all the time, but it really does provide a powerful way to kind of bring things into alignment, and you can plot things by it. So I know we've talked about, sometimes scale can be a real issue, and how do you handle that? So what the thing to know is that this so-called z-score or normal score or standard score, those all mean the same thing. And what they are is they are actually they are the number that corresponds to the number of standard deviations away from the mean of a particular reading. So if I want to know the z-score, how many standard deviations away from the mean a particular score is, all I have to do is take the difference between the reading and the mean. So for example, how unusual is a 99% graduation rate within this current distribution? Well, the difference between 99% and 81% is 18, or 0.18, right? So all I have to do is say 0.18 divided by the standard deviation, which is 0.13, and I know that the normal score of that is 1.38. So somewhat unusual, not wildly unusual, but I can do the same thing with any of these values. And so when you see, so again, that normal score gives you a way of saying how far away from the average is this data point, and therefore how unusual might we consider it to be. That is all for this. For this section, we'll be looking at these together in class and kind of cover the formulas a little bit more in depth, and also the concepts. So we're going to be talking about these a lot over the course of this week, because obviously these are all formulas that you can have the computer do for you, and you can always look up the exact descriptions of how to calculate these things. But the really important thing is understanding what they mean, because it's through that understanding, of course, that you're going to be able to apply them where appropriate in your work. So I will see you guys on Thursday. Hope everyone had a good spring break. And yeah, see you Thursday morning in room 607C. They switched it around on us. So I will see you guys then.